Welcome back. Today we're going to be talking about compound events and sample space. Our content objective is students will be able to find the sample space when dealing with compound events. Our language objective is students will be able to use correct vocabulary when discussing probability. And why am I learning this? Well, it's important for real-world examples like choosing a dinner and dessert from a menu. So let's go over some background knowledge real quick. We do want to discuss for this particular lesson what is a sample space. We got to remember, a sample space is the set of all possible outcomes of an experiment. Okay, so the sample space for flipping a coin would be heads or tails because that's all the possible outcomes. The sample space for rolling a number cube is 1, 2, 3, 4, 5, 6 because those are the different possible outcomes of that experiment. Okay, so we know probability basically describes the number of desirable outcomes over the total number of outcomes. And we've discussed what theoretical probability is. It's what should happen. It's basically what we expect to happen in theory, hence the name, theoretical probability. Now, what happens when you want to find the probability of more than one thing at once? Well, that's called a compound event. Okay, it's basically the probability of two or more things happening at once. So to find the sample space, we will use tables, lists, or tree diagrams to help us. Now you must use one of them, okay? You need to pick one. An experiment consists of flipping two coins. What's the probability of one head and one tail? So the first one, what we're going to have to do is determine the sample space. So I'm going to go ahead and construct a table first. So here we're going to do, what if the first coin's head, second coin's head, or first coin's head, second coin's tail, first coin's tail, second coin's head, or maybe both coins are tails. So notice this is all the different possibilities that there are. So after a table, let's see, what if you wanted to use a list? We can list them out as heads and heads, heads and tails, tails and heads, tails and tails. Then we talked about, you can also use a tree diagram. So here, if you have heads and tails, from the heads you can have heads or tails. Okay, so notice I'm listing them out as I go. And this is just a good visual for me. Okay, so here, how about tails? Well, tails could be tails and heads or tails and tails, like so. So now back to the question. It did ask, what's the probability of getting one head and one tail? So out of the four different outcomes, I'm noticing that one's one head and one tail. This one's one head and one tail. So I notice there's 2 out of 4. Okay, well now let's take a look at the list. That one's one head and one tail. That one's one head and one tail. It's 2 out of 4. Here, this is one head, one tail. This is one head and one tail. So this is, once again, 2 out of 4. So it doesn't really matter which method you use. You're still going to get the same answer. So the answer would be there's 2 different outcomes with a total of 4. That's your sample space amount. So I'm going to write my probability is 2 out of 4, which will reduce to 1/2. Okay, so the total number of outcomes. Well, we know from the first coin there's 2. There's heads or tails. And then for coin number 2, it's also heads or tails, which is 2 outcomes. Now what you could do is do 2 times 2, which gives you 4, because there are 4 total outcomes. Doing this is applying the fundamental counting principle. When there are m ways to do one thing, in this case, 2 outcomes, and n ways to do another thing, 2 outcomes, then there are m times n ways of doing both. So 2 outcomes from coin 1, 2 outcomes from coin 2, multiply it and you get 4 total outcomes. So why? Why would I want to use the fundamental counting principle? Well, sometimes knowing the total number of outcomes before you begin finding the sample space helps. Okay? Understanding this will allow you to determine the denominator of your fraction. How much is it out of? Okay? So, looking at this one, number 2. An experiment consists of flipping 2 coins, okay, which we already determined the different outcomes for that. What's the probability of both tails? Well, in the table, I see that there's 1 out of 4. In the list, I see there's 1 out of 4. And in the tree diagram, I see that there's 1 out of 4. So I'm going to say that there is 1 outcome in the events of both tails. So I'm going to say that probability is 1 out of 4. So notice, using one of these methods is going to definitely give you a visual so that you come to your conclusion no matter what question they ask. Okay, now let's spruce it up. Number 3 is asking us to conduct an experiment that consists of rolling 2 fair number cubes, or in other words, dice. They're asking us to find the probability that the sum is equal to 7. So what I'm first going to do is create a table that follows the requirements, which is I need the 2 numbers to add up to 7. So I'm going to do, let's see, 1 and 6, 2 and 5, 3 and 4. Okay, and now I can switch. Now what if number cube 1 was 4 and then number cube was a 3? Then here, what if it's 5 and a 2, 6 and a 1 here? So notice that's all the different possibilities to get a sum of 7. So you can construct this table as a list. 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, 6 and 1. Okay? So when rolling 2 number cubes, how many total possible outcomes are there? Okay? Well, let's apply the fundamental counting principle. Okay? There are 6 outcomes from cube number 1, 1, 2, 3, 4, 5, 6. And then there are 6 outcomes for the second number cube, 1, 2, 3, 4, 5, 6. So using the fundamental counting principle, I'm going to do 6 times 6, which is 36 outcomes. So that's going to definitely be the denominator in my fraction. But how many different ways were there? Well, let's count. 1, 2, 3, 4, 5, 6. So notice there's 6 ways out of 36 total outcomes. So I'm going to go ahead and say that the answer is 1/6. And why? Because you need to make sure you're reducing your fractions. I noticed both numerator and denominator could be divided by 6, and that's what gave me 1. 6 divided by 6 is 1. 36 divided by 6 is 6. Okay, now some of you might have asked, well, what about a tree diagram? A tree diagram is going to work, but it might be a little more work than a list and a table. So notice you would have to do this. 1 for assuming the first number cube would be a 1 and all the different possibilities. What if your number cube was a 2? All different possibilities. What if your first number cube was a 3? All the possibilities. So you understand and you can even see that this is a little bit more work than the other 2 options. However, a tree diagram is great for showing you all the possible outcomes. That way you don't accidentally miss any. Now, in order to determine the sample space, what else could have I done? I could have used a diagram with actual visuals, like here, look. I could have gone a 1 and a 1, a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1 and a 5, a 1 and a 6. And now let's try 2. A 2 and a 1, a 2 and a 2, a 2 and a 3, a 2 and a 4, 2 and a 5, 2 and a 6. This allows it to be so structured so that you know every single possible outcome. Okay, so here I can find all the ones that add to 7. This adds up to 7, this one adds up to 7, this one adds up to 7, that one adds up to 7, this one adds up to 7, and this one adds up to 7. So even here you can see there's 1, 2, 3, 4, 5, 6 that add up to 7. And then here there's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So 6 by 6 is 36. So it is out of a total of 36 options. Okay, so now the question is, what's the probability of it at least 1/5 is shown? Okay, so with a table, I'm going to go ahead and list, well, I can have a 1 and a 5, a 2 and a 5, a 3 and a 5, a 4 and a 5, 5 and a 1, 5 and a 2, 5 and a 3, 5 and a 4, and let's not forget 5 and 5. Now notice here I went 1 and 5, and then later I switched it to 5 and 1. Now notice here we have 5 and 5. Do you think it matters if I switch it to 5 and 5? Should that create another row? The answer is no, because 5 and 5 is exactly the same as 5 and 5, so I'm not going to double count that. Now, there is 5 and 6, and then 6 and 5. Okay, so for a list, you would go through the same thing. You would list them all out. So it's very similar to a table. It's just whatever you're more comfortable with. And then, in order to determine the sample space, the total number of outcomes, I'm going to go ahead and say there's 6 options for cube 1, 6 outcomes for cube 2, so altogether there are 36 outcomes. Now, of those 36, how many of them actually had 5 show up at least once? Well, let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I would say it's 11 out of 36. Now, for a visual with the actual number cube, you can see here, I would include all of the 5s. Okay, so here, this one had a 5, this one had a 5, this one, that one, this one, this one, this one, this one, this one, this one, and that one. So notice all of these have a 5 showing up at least once. Okay, if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 total out of 36 altogether. Okay, so now what's the probability of getting double 6s with the 2 number cubes? Well, the sample space is going to be the same. Now we're going to look, how many different ways can we get double 6s? I only see 1. So my answer would be 1 out of 36. Okay, so now moving on to number 6. It says, finding sample space using tree diagrams. Garcia has a quarter, a dime, and a nickel in his left pocket. In his right pocket, he has a blue marble and a red marble. If he selects a coin from his left pocket and a marble from his right, what's the probability that he's holding a dime and a blue marble? So first, starting with the tree diagram, I'm going to go ahead and figure out what different coins could I have. Well, Garcia can either pick from a quarter, a dime, or a nickel. Now, not only does he have coins, but he also has marbles. So let's go ahead and take a look at the marbles. He has 2 colors. He has a blue marble and a red marble. So here, you could have gotten a quarter with the blue marble or a quarter with the red marble. A dime with the blue marble or a dime with the red marble. A nickel with the blue marble or a nickel with the red marble. So again, you can always construct a list as well. You could have said, okay, quarter blue, quarter red, dime blue, dime red, nickel blue, nickel red, right? But to go back to the question, it says, what is the probability that he's holding a dime and a blue marble? I'm going to look through my options. So first he had to pick a dime. Okay, so here, I'm focused here. And from that dime, he also picked a blue marble. So this is the only option. So you could look at it using this tree diagram, or you can look at it using this list. You can see that there's only one option regardless. 1 dime, 1 blue. So, but how many total outcomes are there? Well, let's use the fundamental counting principle. Let's remember there are 3 different outcomes for the coins, and there's 2 different outcomes for the marbles. So 3 times 2 is going to give me 6. Now some of you might be asking, well, why am I using the fundamental counting principle when I can definitely see it from my tree diagram or from my list? Well, it gives us a great way to look at, making sure that we don't miss anything. But also, sometimes if the numbers were larger, we might not want to go through all of the different possibilities. So the fundamental counting principle is actually very helpful. So keep that in mind. But to answer the question, we can see that there is 1 out of 6 different ways, so my probability is 1/6. Now, let's go ahead and try another example. It says finding a sample space using tree diagrams. On her bookshelf, Lisa has 4 math books numbered from 1 to 4. On the first shelf, she has 3 puzzles labeled A to C. On the second shelf, if she chooses a book and a puzzle at random, what is the probability of getting a book with an odd number and a puzzle labeled C? So first we know that she has some math books, right? We have math books anywhere from 1 to 4. But not only does she have math books, she has puzzles. She has puzzles labeled from A to C, meaning there's A, B, and C. So I'm going to go ahead and create a tree diagram and say if she picked book 1, she might have chosen puzzle A, puzzle B, or puzzle C. If she chose book 2, she could have chosen puzzle A, B, or C. And I'm going to repeat this for each book. Okay. Now you could list it because it's nice to have them listed out. You could have said 1A, 1B, 1C, 2A, 2B, 2C, 3A, 3B, 3C, 4A, 4B, 4C, etc. Now to get back to the question, it says, what's the probability of getting a book with an odd number and a puzzle labeled C? So notice, odd number labeled C. That's an odd number with a C. That one's not an odd number. This one's an odd number. That one's not an odd number. So notice there's going to be 2 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 2 out of 12. Now, if you didn't know about the 12, you could have used the fundamental counting principle and say, okay, there's 4 math books, and there's 3 different puzzles. So I'm going to do 4 times 3, which gives me 12. So the answer would be the probability is 2 out of 12, which reduces to 1/6. So again, if you're wondering, how did I get 1/6? It's because there's technically 2 out of 12. If you reduce both the numerator and denominator by a 2, you will end up with 1/6. Now for number 8, what I'd like you to do is go ahead and pause the video and try number 8 by yourself. Okay, so let's see how well we did. Number 8 says, what's the probability of rolling an even number on a number cube and tossing a tail on a coin? So this one, I'm going to construct my tree diagram a little bit different, so I want you to take a close look. I'm going to go ahead and take a look at the number cube and then the coin. And then we're going to go ahead and take a look at the list. So first, I'm going to go ahead and list all the possibilities for a cube, which is 1 through 6. And then from the 6, I know from the coin you can either get 1 heads, 1 tails, 2 heads, 2 tails, 3 heads, 3 tails, etc., all the way down. So as I list it, it's going to be 1, head, 1, tail, 2, heads, 2, tail, etc. So this is nice because then I can visually see all the different possibilities. I can figure out the sample space. Now the question was, what's the probability of rolling an even number on a number cube and tossing tails? So I'm looking for even numbers and tails. Nope, 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 yes, no, 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 yes, no, 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 yes. Okay, so I noticed that there's 3, but I need to figure out what is the total number of outcomes. What's the sample space? What's the amount? Well, you can definitely count these or just understand, okay, there's 6 possibilities from the number cube, there's 2 possibilities from the coin, so altogether there are 12 outcomes. So here, meeting the requirements, there's only 3 out of 12. That gives me 1/4. So again, if you're wondering how I got to 1/4 so quickly, I'm reducing my 3/12 by 3, and that's what gives me 1/4. Guess what? That concludes the lesson for today. Thank you so much for tuning in, and until next time, bye!